All right, let's jump right in. We talk about AI like it's this magical thinking thing. But today, we're going to pull back the curtain. Because behind every smart decision an AI makes, behind every single incredible image it generates, it's not magic, it's math. So, yeah, let's get into it.
So, if we really want to get what makes these things tick, we have to ask a pretty basic question. Forget Python, forget all the code. What's the actual native language of AI? What's it thinking in?
Yep, that's it. Mathematics. It's the universal language of patterns, of structure, of how things change. And in this explainer, we're basically going to learn to speak it, at least the core dialect that brings AI to life. So first up, we're going to explore this secret language. We'll see exactly how these, abstract ideas from math class are actually used to build behaviors that we look at and say, wow, that's intelligent. Okay, so let's start with the absolute basics, the raw material of AI, which is just data, right? But how do you take something messy, like a word or a picture or a sound, and feed it to a machine? Well, you have to translate it into the one thing a computer gets, numbers. Or to be more precise, a single point in space. And that brings us to our first huge idea, the vector. Just think of a vector as the fundamental atom of data in this whole AI universe. It's really just a list of numbers that pins down a piece of data, like a word or a single pixel, as a specific location in some crazy high-dimensional space. This lets the AI actually measure things, like how close or far apart different ideas are. And this gets super practical, super fast. For language models, words like king and queen become vectors that are actually neighbors in this space. For an image, every single pixel is just a vector describing its color. Even the firing of one artificial neuron is just a number in a long vector. Literally everything gets turned into this geometric format. Okay, so we've got our raw material, our data, all neatly packaged up as vectors. So what's next? Well, now we need some machinery to actually do something with it. We need tools that can take all these points of data and start transforming them in useful ways. And enter the matrix. Seriously. If vectors are the data, you can think of matrices as the engines. A matrix is just a grid of numbers, but what it does is transform a vector. It can stretch it, squish it, rotate it, or mash it together with others. It's the active machinery that reshapes this entire data landscape. And check this out. The absolute beating heart of a single layer in a neural network is this simple little equation right here. X is our input, our data vector. And that W, that is the weight matrix. It's a matrix packed with numbers that the AI actually learns. This is the thing that controls which features get amplified and which get ignored. All the knowledge is stored right there, in that matrix. Okay, so we have data as vectors. We have machinery in the form of matrices. But how does the machine figure out which transformations are the right ones? I mean, how does it actually get better at its job? It needs a teacher. It needs a guide. And that guide is calculus, specifically a process called gradient descent. Now, gradient sounds kind of scary, but it's just a term for the direction of the steepest uphill climb, the direction of more error. So to get better, the AI just figures out which way is uphill and takes a tiny step in the exact opposite direction. It just keeps walking downhill, towards less and less error. And this whole thing builds into this beautiful, simple loop that gets repeated millions, maybe billions of times. Step 1, the model makes a guess and measures how wrong it is. That's the error. Step 2, it uses calculus to find the direction that would make that error even worse. Step 3, it nudges its internal weights, that W matrix, in the exact opposite direction. And step 4, it just does it all over again, getting a tiny bit less wrong each and every time. So here's what you need to picture. Imagine this gigantic, hilly landscape. Every spot on that landscape is a different version of the AI's brain, and how high up you are represents how much error you have. The entire goal of training is for the AI to start somewhere high up on a hill and just keep walking downhill until it finds the absolute lowest valley. That low point, that's the best version of the model. All right, let's pull the camera back now and put all these pieces together. We've got our vectors, we've got matrices, and we've got a way for them to learn. How does this all combine into a system that can actually, think? It really boils down to two main characters in this story. On one hand, you have linear algebra. It gives us the stage and the actors, the vectors that represent our data and the matrices that give it structure. But on the other hand, you've got calculus, and calculus is the director. It provides the learning process, that gradient descent, that tells the actors how to get better and better over time. And this right here,
This is the grand unification. AI isn't just one of these things. It's this incredible fusion of all of them working together. You have the geometry of data points, the algebraic structure of the network, and the calculus of learning. All of it has to come together to create what we see as intelligence.
So just stop and think about that for a second. What we call learning isn't some abstract concept here. It is a literal physical journey. The AI is actually moving through a high-dimensional space of every possible answer, and the gradient is its compass, constantly pointing it downhill toward the best one. So let's bring this all home. How do these abstract ideas, vectors, matrices, gradients, how do they actually become the intelligence that we chat with and use every single day? So here's the whole story in a nutshell. We use vectors to represent the world, we use matrices to transform the world, we use linear algebra to build the structure for it all to live in, and we use calculus to let it learn. That's pretty much it. That is the fundamental blueprint for almost all modern AI.
And this brings us to the ultimate takeaway. AI isn't really an attempt to copy the human brain, neuron by neuron. It's actually something more fundamental. It's the behavior that just emerges from a system built out of pure math, whose only goal in life is to get less wrong, to minimize its uncertainty about the world.
There's this quote that just perfectly captures everything we've been talking about. AI is kind of showing us that thinking and learning and even understanding, it all has a shape. It has a geometry. And through this mathematical lens, we're not just building cool tools, we're kind of exploring the very structure of thought itself. Which, leaves us with one last really big question to chew on. If intelligence really is a structure that we can build with math, what does that mean about its limits? Are there any? Or is it as boundless as math itself?